The objective of this video is to show how we can learn the directions of reactions from the analysis of Gibbs free energies. We'll discuss two types of reactions, chemical and physical. Transformations in which molecular composition changes are called chemical reactions. Other transformations, for example, phase transitions, in which it's the structure of the substance that undergoes some kind of change, are considered to be physical processes. So something like melting or boiling. So in this video, we'll see how the second law, captured by Gibbs free energy, which balances heat and disorder, may be used to predict the overall direction of chemical reactions and phase transitions. We'll start with chemical reactions and then go on to talk about phase transitions. All right, when we control temperature and pressure, the free energy that we want to use is the Gibbs free energy. It captures the balance between the enthalpy and entropy. So recall our discussion of enthalpies and the application of the Hess law. From estimating enthalpy changes in course of a reaction, we learned whether it released heat or absorbed heat. It's interesting that a reaction that absorbs heat can still be spontaneous, even though it's endothermic, even though it requires energy input in order to move forward. So clearly the enthalpy is not everything. Entropy plays a deciding role in whether a reaction will proceed or not. This fact is hiding in the title of a famous Ray Bradbury's novel, Fahrenheit 451, which is the temperature at which paper self-ignites, meaning it starts spontaneously reacting with the oxygen in the air. Now, this is my artist's rendition of the possible shape of the Gibbs free energy for the ignition, for the process of burning paper. And what I was going for was that the reaction is not spontaneous at temperatures below 451 Fahrenheit. Then it hits 0 at 451, and beyond that it's spontaneous. So the Gibbs free energy is negative. This is not the true Gibbs free energy. This is just a sketch. All right, so let's see how the standard molar Gibbs free energy of reactions are found from standard molar Gibbs free energies of formation. The standard molar Gibbs free energy of formation is the change in Gibbs free energy that accompanies the formation of 1 mole of substance in its standard state from its constituent elements in their standard state, meaning pressure is 1 bar and temperature is 25 Celsius or 298 Kelvin. The values of the standard molar Gibbs free energy of formation for many compounds are known and freely available in published datasets. For example, in the back of our textbook. All right, so in general, the Gibbs free energy for a reaction, a schematic reaction is shown on the slide, where we have the number of moles in lowercase A, B, C, and D of substances A and B for reactants and C and D for products. For something like this, the Gibbs free energy change for a generic reaction is given by the sum of Gibbs free energy energies of formation for the product. So we see C and D with the plus sign, minus the sum of Gibbs free energies of formation for the reactants. We see them with the minus sign, and of course we need to multiply by the stoichiometric coefficients right here. So it's very similar to what we did with enthalpies, and following the simple focus question, let's take a look at a sample problem that we can tackle by applying this rule and answer a question whether methane is also going to auto-ignite, but at room temperature. All right, so let's compute the Gibbs free energy change for a redox reaction in a combustion process of methane to produce carbon dioxide, gas, and liquid water. So we're going to assume that there's 1 mole of methane and the entire reaction takes place at 25 Celsius and 1 bar pressure. All right, so what we're going to do is we're going to take a look at this reaction in which we have 1 mole of methane gas reacting with 2 moles of oxygen gas, producing 1 mole of carbon dioxide gas and 2 moles of liquid water. We're going to use the definition of the Gibbs free energy change for the reaction as the enthalpy change for the reaction minus temperature times the entropy change for that reaction. And of course, we know how to compute those individual components. We simply are going to compute them separately as the delta H for the reaction under standard conditions by summing the enthalpy contributions from the products and subtracting the enthalpy contributions of the reactants. If we sum these numbers up, the numbers I simply found in the table, but we can also search for them online. The outcome is negative 890.3 kilojoules per mole for the enthalpy change for this reaction. For the entropy, more of the same, we get the number of negative 242.8 joules per mole, not kilojoules, joules per mole. The numbers for this calculation came again from the same table in the back of our textbook, Cheng. And so to put those numbers together, what I'm going to get is the change in the Gibbs free energy in standard conditions for this reactions. I'm going to get minus 890.3 kilojoules per mole for the enthalpy, minus temperature, which is 25 Celsius or 298 Kelvin, times minus 242.8 joules per mole for the entropy change, and we need to divide it by 1,000 to get the units match kilojoules, and the answer is the overall molar Gibbs free standard molar Gibbs free energy for this reaction is very negative. It's negative 818 kilojoules per mole. So we know that a negative free energy change for a process indicates a spontaneous process. So we can infer from this that combustion of methane is spontaneous at room temperature. Now, from our experience, from the experience you might have from cooking in, maybe you have a grill that uses methane, we know that methane doesn't just start burning at room temperature. This is because the change in free energy tells us something about the thermodynamic stability. We know how this reaction is going to go if we let it, if we give it all the time in the world. This is going to be the end game. This is the information that we get from the Gibbs free energy balance. What it doesn't tell us anything about how soon we will see this reaction and how soon we will see this equilibrium situation after we allow the reactants to mix. So when we'll get to the kinetics part of this class, we will discuss this in much more details, and you will understand the reason why methane does not just start burning at room temperature on its own, even though it is the thermodynamically favorable process, as indicated by the negative Gibbs free energy. All right. All right, moving on to phase transitions and non-chemical reactions. Besides chemical reactions, we may be interested to investigate physical transitions, such as phase transitions. One example of a phase transition is the melting and boiling of things. So when a substance melts, it undergoes a transition from solid phase to liquid, and when it boils, it transitions from liquid to gas. We're used to water melting at 0 Celsius and boiling at 100 Celsius. We're used to these particular numbers because our lives take place in more or less constant atmospheric pressure, more or less at the sea level, right? But under different pressure conditions, for example, if we climb a very high mountain, we will notice a change in the melting temperatures and the boiling temperatures of water. This is because the Gibbs free energy, which determines which phase will dominate and which phases will coexist, it depends on both pressure and temperature. On the graph, we see the pressure temperature phase diagram of water. The pink lines that you see indicate the pressure and temperature conditions of phase coexistence. Now, staying at the low temperature, if we just follow this phase diagram, if we start from low temperature, if we go from very low pressure towards higher pressure, what we're going to encounter is the transition from gas or vapor, V is for vapor, into the solid phase of water. So we're going to encounter first the coexistence condition, a temperature and pressure at which solid and gas will coexist, and then the substance will actually transition from gas to solid. If we increase the temperature slightly, and we might arrive at the triple point as we increase the pressure, right? At the triple point, all three phases, the gas, the solid, and the liquid, will actually coexist. So what does it mean that they will coexist, the three of them? For coexistence of two phases, the condition is that the Gibbs free energy in phase 1 is equal to the Gibbs free energy in phase 2. So as we go from vapor to solid, on the pink line, at this particular temperature and that particular pressure, what we have is Gibbs free energy for gas is equal to Gibbs free energy of solid, and the delta G at coexistence is 0. So for a triple point, what we need to, the condition is, of course, the equilibrium between the solid and the liquid, the solid and the gas, and the liquid and the gas. So we have three constraints for the triple point on this phase diagram. All right, so as we continue warming up, we're getting into the regime of gas-liquid transitions. So we can go if we're anywhere here, we simply increase pressure, and we're going to go from gas to liquid. We'll see the condensation of our substance from gas form to liquid form. And interestingly, if we continue increasing temperature and also pressure, somewhere around 650 Kelvin in temperature and 217 atmospheres, not exactly conditions we encounter very often in our daily lives, but nonetheless they exist. What happens is that this coexistence line between liquid and vapor, it ends. It reaches a final point that is called the critical point. What happens beyond this point is that vapor becomes completely indistinguishable from gas, and we call this new phase the supercritical phase. So this isn't some kind of equilibrium between gas and liquid. It's literally that those two phases become indistinguishable from each other, and they are referred to as supercritical fluid. Now, it's interesting that the solid-liquid line, it never stops. And the reason for this is because the transition between solid and liquid, it requires a significant change to the orientations of molecules within the substance. So solids are often crystalline they crystallize, and so all the molecules get very organized in that transition. So it's never possible to go from the ordered crystal to disordered liquid without undergoing a phase transition. But for gas and liquid, there is no ordering in either of those phases. Gas is disordered and liquid is disordered. The only difference is density. And so for high enough temperatures and pressures, turns out that we can reach a state of matter in which there is literally no difference between them. So I know that this is a point that is quite interesting. So I found a very nice illustration of this of the emergence of this supercritical fluid for the CO2 as the substance. And just to put this in context, beyond applications or anything very useful, you might be interested to know that the atmosphere of Venus is about 96% carbon dioxide, and the pressure on Venus, surface pressure, is about close to 100 bar, and the temperature is close to 800 Kelvin. So not exactly very comfortable conditions, but they are precisely the conditions for the supercritical phase of CO2. So if we do an experiment in which we observe the transition of CO2 from gas to the from liquid to the supercritical phase, we might get a glimpse at what the atmosphere in Venus might look like. So maybe something like this: a certain amount of liquid CO2 is placed in a chamber that is capable of withstanding very strong pressures, and it's temperature controlled. So what happens is they put CO2 in the liquid form. The black line here indicates the level of CO2 in the liquid form. The rest is gas. So this is before the temperature is approaching the critical temperature. And then they will increase the temperature, and we will observe the transition from gas-liquid equilibrium to the new supercritical phase. One thing to watch for is that the level of the liquid will not go down. So if it was an evaporation process in which the liquid simply became gas and everything just looks like gas floating in this volume, then you would see the separation between gas and liquid, the surface, go down and eventually disappear. What we will see is that the surface will remain there until it will simply disappear. It will never go down. So that's how we know that it's not just simple evaporation that's happening there. It's the actual transition from gas-liquid equilibrium to a new supercritical phase for the CO2. Let's watch. So we can see the liquid CO2, and they raise the temperature. We can kind of see it in the back. Just watch the surface, and it disappears. It doesn't go down. It simply disappears. Now what we see is a supercritical CO2. And maybe if we ever find a way to visit the Venus atmosphere, we're going to see something like this. And if the temperature drops, maybe it's going to do this. All right, so this is a fun demonstration of the supercritical phase of the CO2. Just to mention some cool applications of this state of matter. Supercritical water is used in dry cleaning because, surprisingly enough, in the supercritical phase, water is suddenly very good at dissolving organic molecules, the very same molecules that are known for their hydrophobicity, and CO2 is actually in practice used to extract caffeine from coffee beans to make decaf coffee. All right, so with this, I'm going to conclude the discussion of the supercritical phase and go back to more down to earth issues, and I'm going to discuss how we construct the phase diagram, present the Clapeyron equation, and then finally settle, or at least make some progress in settling the question of how does skating actually work. Okay, so let's try to understand the phase diagram a little better. Matter exists in the state for which the molar Gibbs free energy is the lowest, right? So how do we construct this phase diagram? Well, one way to do it is to start somewhere, find a point that is a coexistent point. So a point would be the combo of pressure and temperature at which at least two phases coexist, right? And then we need to know how the pressure on the coexistence line depends on the temperature. So the constraint is that there's coexistence, and then we change pressure a little bit. We need to find how we need to change the temperature to remain on the coexistence line, or the condition, so that the condition of delta G between the phases is still maintained. So dP by dt, the slope, becomes the object that is quite important. So on the coexistence curve, we have the molar Gibbs free energies equal to each other. And so we can write the balance of Gibbs free energies using the definition of the differential of the Gibbs free energy. Say the bar stands for molar. We have the definition here. It's the negative entropy times dt plus the negative molar volume times dP, and this is molar entropy. And so what we do is we plug this for one phase. So it's, say, phase 2, we're going to call it B, and then we end up with negative entropy, molar entropy for phase B times dt plus the molar volume for the phase B times dP on this side. On that side, since they're equal, we're going to have the same thing for state A, which in this case represents phase 1. So it could be liquid gas or liquid solid, and or any other combination. So this is the this condition re-expressed using the definition of Gibbs free energy in terms of entropies, molar volumes, and pressure and temperature. Right, now we can rearrange this equation to collect all terms that depend that have the dt, multiplying them. So moving minus sb to the other side brings it on this side with a plus sign, so we get sb minus sa. All of this is molar quantities times dt. Both of them are multiplied by dt. And on the other side, we get a vb, the molar volume for phase B. And then VA is going to come with the negative sign, so it's going to be VB minus VA times their common multiplier, the change in pressure, dP. So SB minus SA is delta S, the change of entropies between the two phases. VB minus VA is delta V, the change in molar volumes between the two phases. And so to get the dP by dt, I simply move dt to this side of the equation. I divide both sides by dt, and then I divide both sides by VB minus VA, or delta V, and I end up with this form of with this equation, which is completely true and general for any pressure or temperature. So we have the slope of the pressure function with respect to temperature on the coexistence line, where two or more phases coexist, is given by the change in entropy between the two phases divided by the change in molar volume between the two phases. For a more specific case, a more restricted case where, for example, the pressure is constant, we can say even more about this equation, about this relationship, and we can equate the change in entropy with enthalpic change divided by temperature. right? As we've seen before, at constant pressure, the change in entropy is just enthalpy divided by T. And so we get that the slope of these lines is given by the enthalpy change divided by temperature divided by the change in molar volume. And that is what people refer to as Clapeyron equation. Now, let's see whether we can maybe do things a little simpler, a little bit more visual for us. Let's forget about the slopes and simply construct a phase diagram 1 point at a time. So 1 point at a time means that I will fix pressure at some value, and I'm going to plot the Gibbs free energy for the different phases. So as a function of temperature. So I'm going to have the molar Gibbs free energy for the solid phase at a fixed pressure P1. This is going to be the line. And I'm going to plot molar Gibbs free energy for the liquid phase at the same pressure P1. And this is going to be the line. And I'm going to plot the molar Gibbs free energy for the vapor phase, the gas phase, at the same pressure P1. This is going to be the line. And now the intersections of those two, of each pair of lines, are going to tell me where those two phases coexist, right? So solid and liquid coexist at pressure P1 and a particular temperature we're going to call, well, in the textbook they call it TF. I would call it T melt for clarity. It's probably TF for some kind of historical reasons. Now, temperature for boiling or going from liquid to gas comes from the intersection of this line with that one, with that line, and that gives me a temperature I'm going to call TB or T boiling. Now I can change, and that's going to give me a point here somewhere, and a point at a higher temperature but the same pressure, right? So I'm going to get a point somewhere there if it exists. And then I repeat this for another pressure. So I can choose a different pressure and do the same once again. All right, and so keeping track of PT pairs for on the coexistence line that for which the Gibbs free energies, molar Gibbs free energies of two phases are equal, one by one, point after point, we'll construct this diagram for any substance. All right, so hopefully this protocol is a little more easier to imagine than getting the slopes and constructing the curve that way. Let's take a look at a quick question about this. And finally, we're going to tackle one more problem, and we're going to tackle the question, is skating possible because of melting point suppression? All right, let's see how we can use the Clapeyron equation to find out by how much the melting temperature of the ice directly under a skater is suppressed due to the pressure applied by the weight of the skater through the skating blades, right? So one theory of how skating works says that ice melts under the blades because the melting point is suppressed sufficiently for it to melt even in freezing temperatures, making the ice slippery and skating possible. Another theory says that the ice melts due to friction. Well, it's not easy to settle this question, but we will give it a shot. We're going to use the Clapeyron equation to find out whether the melting point suppression could be sufficient to make skating possible, even at very common and very moderate negative temperatures of, say, -5 Celsius, which clearly happens a lot in Canada, and we definitely know that skating is possible. Now the question is whether the melting point is actually suppressed beyond 5 degrees Celsius, and that's why the skating the ice becomes more slippery and we can skate. Let's find out. So we want to know how much temperature will change because of a change in pressure that we're applying through the skates. So we're looking for dt by dp, right? That's what we're looking for. Now, Clapeyron equation gives us dp by dt. And to get dt by dp, we're going to use this little trick and say that dt by dp is actually we need to invert the dp by dt. So we're going to do 1 over just the fractions, the same way that fractions work. 1 over dp by dt is going to propel dt to the top of this fraction. We're going to get dt by dp. All right, we know a lot about derivative of pressure with respect to temperature from the Clapeyron equation in terms of physical quantities such as enthalpy and molar volume changes. And so this is something that we can actually compute for a physical quantity, and then we're going to invert it to get the change in temperature. All right, let's calculate the slope of the solid-liquid coexistence line at the melting temperature of ice, which is 273.15 degrees Kelvin. And we know that the enthalpy of fusion is 6.01 kilojoules per mole, and the molar volume, the change in molar volume in this fusion process is just the difference between liquid phase minus the molar volume in the solid state, and we have the numbers 0.018 liquid liters per mole and for the liquid molar volume, and 0.0196 liters per mole for the solid state. We plug those numbers in and we get a very nice round number for dp by dt, and this is minus 136 atmospheres per Kelvin. Now, to get dt by dp, I'm going to invert it. So I'm going to take 1 over whatever I got here. It's going to be minus 1 over 36. And now to get dt, which is the change in temperature, the melting temperature, because we're changing pressure, I will simply multiply this by essentially both sides of this equation by dp. And I'm going to get dt equals to minus 1 over 36 times the change in pressure, dp. Now the question is just how much pressure does a person apply through the skates, through the blades on the ice when they are skating, and the pressure that we apply apparently is on the order of 10 atmospheres. So the change in pressure, and I guess that includes the atmospheric pressure. So the change in pressure is 10 minus 1, we want 1 for the atmospheric pressure. And so it's minus 9. I'm going to replace dp with 9 atmospheres divided by 136. Take the negative of that number. The units for this are Kelvin. And what I get is that the temperature, the melting point, is going to be suppressed by 0.06 Kelvin, which is clearly not enough to bring the melting point below negative 5 Celsius, right? So the conclusion from this is that it's clearly insufficient to make the ice melt due to pressure of the skates when it's minus 5 Celsius outside. The corresponding temperature in Kelvin is 273.15 minus 5. We get 268.15. We are definitely not going to get there with such small suppression. And so our quick calculation tells us that the theory that skating is possible due to the ice melting because of the weight of the skater applying pressure on it is more or less busted. So the other theory was that the melting is caused by friction. The mechanism for this is not exactly known. But at least we know that the skating is not being made possible through melting temperature suppression. All right, so a quick intuition for the melting point suppression altogether. I would like to tell you that the intuition behind this is due to the fact that applying pressure favors the more dense phase. So the denser phase is more favorable under stronger pressure conditions. And this turns out to be for water, not the solid state, but the liquid phase. And that's very interesting because the liquid water is, we all know that liquid water around the melting point is denser than the ice. That's why ice always floats at the top of water. So water under higher pressure would require lower temperature to crystallize. All right, with this, I'm going to conclude this video. And see ya.